Hey guys, welcome back to Explore Electronics Plus. This video is about understanding Verilog concepts from beginner level to the advanced level. Let us get in and see these topics. The very first thing is starting from the introduction, then data types and operators in Verilog, different modeling styles in Verilog to design combinational and sequential circuits, then design of submodules and instantiation of those to create a complex module, then utilizing task and functions of Verilog to repetitively do some functionality in the module. Then let us do a memory design and also verify this using Verilog Testbench. Then the very first thing is introduction to Verilog. What is Verilog? Verilog is an HDL language. It is hardware description language. The name says we are going to use this for model digital systems by coding its functionality. The functionality will be written in the line of codes like this, and once we synthesize this, we will be getting the hardware which will be consisting of gates like this. This is what the main intention of Verilog is. Why this Verilog is so important in hardware design then? Because of it is going to represent the hardware directly, but we will be writing its functionality in a code. And then what we do, we will do simulation and verification. We can simulate the code what we have written and see whether the design what we have made will be satisfying our functionality or not, using waveforms as well as the print statements, and by giving some stimulus to that particular design we can verify it. That is what simulation and verification is. Then comes the synthesis. Once the design is simulating properly for the functionality what we have designed, then we can convert that high level description code into a gate level representation. So the lines of code what we have written that give us the hardware circuit itself, and this circuit may be something generated like this. So this is the exact hardware what we are going to implement it on a silicon for IC. That is the major advantage of going for Verilog for design. Then we need to understand what is the basic syntax of that Verilog module. If you take any Verilog module, you can see here it will start with a keyword called module. This is the starting point of Verilog code, where this indicates a basic building block. Suppose an AND gate is going to be designed, this will be a module. This module will be having a name called AND gate, right? That name will be given over here. You can see the AND gate name in the example. This AND gate will be having input and outputs that will be called as ports. That port list will be done after the name is given, and then they will be having the directions as input and output. That will be port directions we are going to write as soon as we do the module and the port list. Here you can see in the example we have combined the port names as well as the directions. After the name of the module is given, input A, input B, output C are the ports of this particular module. Then comes the parameter declaration. Here if any parameters are required to fix some values to particular keywords, then we can do using parameters. Then comes include directives. The submodules need to be included to create a top module, or any files need to be included with this module can be done using tick include directives. And then the major part of the Verilog is the logic implementation with respect to the functionality over here. We can use variable declaration, we can use some assignment statements, we can do by instantiating the lower modules, we can do by using initial and always blocks, or we can use task and functions of the Verilog. Then we need to end this module with a end module. If you look at the simple example over here, here it is module keyword, name of the module. These are the ports. There are 3 ports here. Out of those 2 are inputs. Then the functionality of this AND gate will be implemented with the behavior of that is C is equal to A and B is the behavior. And that will be defined using assign keyword. It is assigning A and B computation to the variable C, and once we synthesize this gives us a AND gate is the hardware which is going to be the hardware in the IC. This is how a basic syntax of any module look like, and these are all the different constructs of Verilog we are going to use inside a module. Then we need to understand which are all the different data types and operators in Verilog. The major 2 data types we are generally using in Verilog is net type and reg type. Net type is a wire, means the keyword we are going to represent net type is wire. Suppose if we represent wire A, by default it will be having a state of Z, means high impedance state. If you represent a register, it will be used to store a single bit of value over a time, and we are going to use these registers in a procedural block, that is in always and initials, and the default value of the register is X. This we need to remember carefully. X is a default value of a register type and Z is a default value of wire type or net type. Generally, all the input variables what we are going to have in our modules will be a net type, and if we are going to use the outputs in any procedural blocks, then outputs need to be represented as registers. Also, we will be having integers and real data types in our Verilog. It will support. If you want any integer value, by default it will take a 32-bit signed number into that register, into that integer. Similarly, floating values can be given by assigning that variable as real type. Here is the example you can see. Module example is the name of the module. Here the inputs are clock, input A, B and output is C. Here we are declaring internal register and internal wire here for just for the connection purpose, that is W and R. If you use a continuous assignment like this is assign statement. This assign statement can be used in this way. At the left hand side means to which variable we are assigning, that can be a wire, and at the right side what we have, that can also be a wire. We should not use a register component at the left side when we are using assign keyword. Then comes the other method of assignment, that is using always. That will be called as procedural assignment. In the procedural assignment, we will be using a keyword called always, and we will be having a set of block of code that will be executed when this part of the variables changes. Means we say always at the rate, we will be having some list of input variables we will be writing here. This will be called as sensitivity list. Means our module or the logic what we have written under this will be sensitive to change in any of the parameters we have listed here. In our example, we have listed positive edge of clock is a very important parameter and sensitive to our design is sensitive to that. So whenever the positive edge of clock comes, whatever the value present in A will be updated to R. Here we are writing this line of code in always statement, means this left hand side operator should be a register. You can see inside a module this is R. We can also use output C over here. C is equal to A or A and with or something like that, but this C should be a register if we are using inside always. Then we need to come and declare here as reg C separately, or at the time of declaration itself we can make it as output reg C. That is what a simple understanding between the continuous and procedural assignment. In the subsequent discussion, let us understand more about that. Then here is the operators in Verilog. Since Verilog is a hardware descriptive language, to describe the hardware we require all the different gate functionality over here, and also we may require some other operators like relational operators, arithmetic operators and shift operators. You can see in the logical operators we will be having bitwise operators and then logical operators as well. These bitwise operators will work on the bits of the two variables. Suppose if the variables are having 0, 1, 1 and 0, 0, 1, if we are going to do the AND operation between these two, these are going to be work on each and every bits. The 0th position will be having 1, 1, AND operation give the output 1. Then it comes to the first position, it will be having 1, 0, the output will be 0. For 0, 0, output will be 0. Likewise, each and every bit will be taken for the computation in bitwise operators. Then comes the logical operator. In the logical operator here you can see double ampersand, double pipe and an exclamatory symbol representing boolean and or and not. These will check for whether the variable, suppose if we do A and B, if this is true and this is true, it means other than 0, it will be considered that as 1, 1 and give us the result as 1. Suppose if we use logical OR, it will check for whether any one of the input is other than 0 and produce the output 1. 1 bit result these boolean logical operators are going to provide, and if you want to go with the bitwise, then a single ampersand, pipe or XOR operator cap like this can be used. And also we will be having some reduction operators. This can be used with a single operand. Then we have shift operators as well, arithmetic operators, and the relational operators to check the equality are greater than, like that. And also we will be having concatenation and replication operators as we seen in any other programming language. And let us see an example over here. Module adder, it has an input 3 down to 0 a, 3 down to 0 representation of a. Here it gives us a of 3, a of 2, a of 1 and a of 0. So a of 3, a of 2, a of 1 and a of 0 indicates this is a 4-bit number. Suppose if we assign a is equal to 1010, here this is a of 0, this is a of 1, this is a of 2, this is a of 3. That is how the vector representation will be done with a MSB first, and we are representing the LSB. So this gives us a 4-bit variable. And similarly B is also a 4-bit variable here, sum is also a 4-bit variable. Then we have an cout, that is 1 bit. Then we can directly use assign keyword here. Assign, with the concatenation we are representing the carry and sum. Here 4-bit sum will be generated and single bit carry will be generated to cout. This is a plus b. This is a simple assignment operator over here. In the subsequent discussion, let us see the different ways of doing the assignment as well. Then comes assignments in Verilog. So as I said, we will be having two types of assignment. One is continuous assignment, another one is procedural assignment. In the continuous assignment, we will be using assign keyword, and when we are assigning any value y is equal to a plus b, this y will be always a wire and ab can be a register or wire. But while using the procedural assignment, we need to use always block or initial block. Always in the sense we will be using always like this, and at the rate we will be providing the sensitivity parameters over here. And suppose if the design is sensitive to a b, we will be writing a comma b here. Suppose if you are doing this with a sequential circuit, we will be writing clock over here. Means with respect to clock, whatever the logic we are going to write over here will be sensitive. So that is the procedural assignment and the continuous assignment. In the continuous assignment, keyword assign and an expression will be used. In the procedural assignment, always and initial will be used. Within always block, we will be not using a always keyword over here, right? And that is what we said here. Outside procedural blocks, we are supposed to write this always. We should not include the continuous assignment inside a always block. And this drives onto nets, means a will be a wire over here. A is equal to b and c we have written. So here a will be a wire, b and c can be a wire or register. But in the always block, whatever the statements we are going to write, something like y is equal to a plus b, here y should be a register and ab can be a register or wire over here. This is a simple difference about continuous assignment and procedural assignment. When we are going to use these, we will come to know how actually the application will be. Next comes modeling styles in Verilog. We will be having different modeling styles. We will be having three major categories over there, that is gate level description, behavioral description and data flow description. Gate level description in the sense, as the name says, we will be using logic gate primitives directly. In Verilog, we will be having a gate primitives which will give us the functionality of logic gates already implemented in a library. And data flow description will be using are the expressions which will be giving the functionality of the design which we are going to write. And in the behavioral description, we are going to write the code in terms of different constructs of Verilog which give us the behavior of the design directly. We will be not directly writing the expressions, we will be not directly writing the gate level representation over here. We will be not using the gate primitives as well. That is behavioral description. So behavior of the design is taken and writing the code by using if else, case, while loops, for loops like that. Then we call it as a behavioral description, and this is the highest level of description in Verilog. Gate level description is the lowest level of description in Verilog. If you look at the gate level description which is written for 2:1 mux here, this 2:1 mux will be having AB inputs, select line is input and Y is output. To implement this 2:1 mux in a Verilog code, to get a hardware of 2:1 mux, there are many different ways to write. One is by using a gate primitives like this. Means this 2:1 mux requires two AND gates. Okay, first AND gate will be given with A and select bar, and second AND gate will be given with B and select input is equal to 1. And this gives us A into S bar and this gives us B into S, and having the OR gate out of these two will give us the output Y. This is the simple gate level implementation of a 2:1 mux. As we have a gate level structure, similarly if you implement in a Verilog code, that is gate level description. And while writing the gates over here, you can see this is one NOT gate required to generate select bar. So select is the input and output is NOT underscore select. Here NOT underscore select will be an internal variable as wire. And by using AND gate, A and D is the keyword for that, and AND1 is the internal variable which is representing output of this AND gate, and similarly AND2. For the input of this first AND gate, we are giving A and not select, and the input of this second AND gate will be giving B and select. So that is how we are going to write the gate primitives. First we will be writing the output, and then we will be writing the inputs required for that. So if you want to implement one AND gate like this, suppose this AND gate will be having A, B and Y, our code will be consisting of A and D and then within the braces Y, comma A, comma B. That is how it goes. Then comes the data flow description, where we will be using the expressions directly. The expression for this 2:1 mux is Y is equal to A into select bar plus B into select. This is an expression now. Directly by using a assign keyword, by writing assign, then Y is equal to, we can write it as A and with not of S, that is S bar, or we will be writing B and with S. This is the expression we can write. But other than writing this expression directly, in our example we have used another method called conditional operator. Here the conditional operator is that first we will be having a condition over here, then a question mark. If this condition is true, whatever written over here will be assigned to Y or the output, or if this condition fails, whatever we written at the after the colon will be the output. This is how conditional operator can be used. Will also be called as ternary operator. Then comes the behavioral description code for the 2:1 mux. Here we will be not using any gates, and also we are not using the expressions. You can see we are using the procedural statements here, that is always, at the rate. We will be using the sensitivity parameters as select or A or B. Select A and B are the sensitivity parameters. If those changes, the output changes. Then comes if select Y is equal to B, else Y is equal to A. This is a comment which I am written. Don't worry about this. This is a comment, right? The only part of the code is if select Y is equal to B, else Y is equal to A. This is a simple code we have written within always. Whenever the value of select or A or B changes, this part of the code will be executed once. So we say whenever select changes or A changes and B changes, we need to execute this if Y, else and Y is equal to A part. This will be written inside a begin and end block. This always block can be used, and depending on the behavior of the 2:1 mux, we have written the code here. So we call it as behavioral description. Then we have one more example here to understand more about the behavioral description, that is 8:1 mux. In 8:1 mux, we will be having 8 inputs and we will be having single output. And to select these 8 inputs as output, we have a select line. Means multiplexer is a device, it will select a single input as a output at a time. So to choose those, we will be having select lines. Since there are 8 inputs, we require 3-bit select line. Select lines values will go from 000 to 111. When a select line is 000, D0 will be selected as output. Select line is 001, D1 will be the output. Select line is 010 means D of 2 will be the output. Similarly, it goes when 111, D of 7. So to have these different cases of inputs of select line and input values, we can use a case statement easily. What case statement says? Before that, module mux 8:1 behavioral is the name of the module. Input wire 7 down to 0D, input wire 2 down to 0 select. Here we can write a wire or we can neglect this. Why? Because by default, these input variables what we have here D and select are wires in Verilog. Okay. Then directly represent output register Y. Since we are using a always block here, we need to write this output as reg by default. Then comes always at star. This star gives us the meaning that within the braces we will be writing D and select as well. right? Other than writing all the inputs with commas, or generally we will be writing with R over here, we can write a star. This star indicating all the input variables will be added in the sensitivity list over here. That is the meaning of using a star over here. Then comes the select cases. Case select. If the select line is having 3 tick B000, means 3 bit 3 tick binary 000, y will be equal to d of 0. This is the first case. If this case fails, it will go to the second line and execute. It will try to select when the select line is 001, y is equal to d of 1. Then it will look for 010 and d of 2 will be assigned to y. Similarly, how many number of cases we have, that many number of lines of code we can write under the case block. Then the last value will be 111, d of 7 will be assigned to y. If any of these not selected, then these are not our cases. Suppose if we give any other value, we will be having a default statement over here. This default value will be assigned to the output. This is the case statement which will be very much helpful when implementing finite state machines. This finite state machines will be having certain number of states, right? State 1, state 2, state 3, state 5, like that. In these states, we need to have some implementation, means directly here how we taken the select lines over here, we can take the states. State 1, this should be the logic. State 2, this should be the logic. State 3, this should be the logic, like that. Case statements will be useful in implementing the FSMs. We have one more example here, that is priority encoder, 8 to 3 priority encoder. Here 8 bits of inputs will be there and 3 bit of output is there, and one input is a valid input. Means whenever the valid input comes, then only we say valid is equal to 1. So the behavior of the priority encoder is that here we will be having 8 inputs that should be encoded to 3 depending on the priority. Here out of 8 inputs, the 7th bit will be having the highest priority and the 0th bit will be having the lowest priority. Means out of these 7 bits, we will be having, suppose 1 will be there in the MSB, we will be not looking for all the lower variables values, and we will be encoding to 111. Here is the meaning of that. You can see in the truth table, first bit is 1, that is MSB, and all other can be treated as 0 even if any bits are there, that is 111 encoded to 111. Suppose if the MSB bit is having 0, then we need to look for the second priority, highest priority one, that is 6th bit. If this is 1, if this is 1 and all other lower bits can be treated as 0, and it will be encoded to 110. So to do that, we need to give the priority in our code in such a way that first we need to check I of 7 whether it is 1 or not. Then we will be not checking I of 6, I of 5, I of 4, 3, 2, 1, 0, right? So we can use a if-else statements in this case. Within always at star, we can start with begin and finally ending with end. We can write a if statement over here. If first I am checking the highest priority one, that is in of 7. If in of 7 is 1, we will be encoding the output to 111. Suppose in of 7 is 0, then only we need to look for in of 6, correct? Then output will be encoded to 110. Suppose if this is also 0, then only we need to look for in of 5. This is the priority level we have given. 7 will be having the highest priority, 6 will be having the next highest priority, 5 will be having the next highest priority, like that. If you want to execute this particular line, all these I of 7, I of 6, I of 5, I of 4 should be 0. That is how the priorities will be assigned, and depending on the priority, we will be assigning the outputs with respect to the encoding method. This can be implemented, this priority encoder implemented using if-else statements. We can also implement using case X. Why case X is required? Why not case statement here? Means case X allow us to assign the values, whatever comes as input, directly map it to X. Suppose if we use a case X over here, case X of input, and here is the first statement of the case. What we have written is, suppose 8 tick B 1 and all other 6 values are XXX. It means the 7th value is 1 and all other bits are any value. It can be 1 like 0, 0, 1, 0, 1, like this. If this is 1, if the first bit is 1, it will consider these bits as X, it will not consider. Then it will directly encode to 111. Suppose if you want to check for the next priority value, suppose the MSP 7th bit is 0 now, we need to look for the 6th bit as 1 or not. In such case, we need to write the second case value as 8 tick B value is 01 and then all the next 5 bits are XX. Then it will encode to 110. This case X statement will be useful in these cases while assigning the priority for the different cases of inputs. We will be having three different types. One is case statement, the next one is case Z statement, and we will be having case X statement. To understand these in a better way, there is a dedicated video made on this in my channel. You can go there and understand it with examples in detail. This will be very much helpful for you guys even in the interviews and also while implementing some designs. Then we need to understand how the sequential circuits will be designed in Verilog. So far we have seen some combinational circuit designs, and also those can be implemented using behavioral description and data flow description. Now comes the sequential circuits. The very basic sequential circuits are flip-flops. In flip-flops, as we know, we will be having a clock signal, reset signal, and we have an input signal and output signal. So whenever the clock will be at the positive edge or in the negative edge, however we are going to design the flip-flop, accordingly the flip-flop will give us the output, right? It will also be called as a 1-bit storage device. So look at the D flip-flop first. In the truth table we have written clock is a positive edge clock. That's why I have shown the upward arrow. This indicates positive edge triggered. Then when reset is equal to 0, let us change this to when reset is 1, this will happen. When reset is 0, this will happen. That is how the implementation is here. When reset is 1, irrespective of my input, Q will be reset to 0 value. When the reset is 0, then only by looking at the inputs, our output will be changed, right? You can see the implementation here. By looking at the truth table, directly we can implement it using a Verilog code. So first module definition, all the input and outputs will be defined. And as we know, the output Q will be always, it should be a register. That's why we represented it as reg. And then comes our implementation, always at the rate pos edge of clock, means positive edge of the clock comes. First we need to look for reset, if reset is equal to 1 or not. If it is 1, Q is equal to 0, else Q will be equal to D. Here we are writing Q less than equals to 0 and Q less than equals to D. It is not a operator which is checking the relation between these two. This is an assignment operator itself. This will be called as a non-blocking assignment operator. Suppose if you write Q is equal to 0 and Q is equal to D, something like that, this using equals, we call it as blocking operator. Let us discuss all those things in the subsequent discussion. So for now, let us understand the D flip-flop in this way. First it will check the reset, then Q will be 0, else means if reset is not 1, Q will be assigned with the value D. This will happen whenever the clock changes. Whenever the positive edge of clock comes, this part of the code will be executed once. Similarly, if you look at the SR flip-flop truth table, S and R are the two input variables here, and the clock will be a positive edge triggered clock here, and reset 1, it will reset the output, and else depending on the SR values, the outputs will be generated. For 0, 0 S and R value, Q will be in the hold state. It means it will be holding the previous value of the output value. Means if S is equal to 0 and R is equal to 0, if the previous value of Q is equal to 1, means in the next positive edge of the clock also, it will be holding this 1 as it is. That means hold state is. Then when S is equal to 0 and R is equal to 1, it will be 0. 1, 0 give us the output 1. 1, 1 is high impedance state, that is Z. Now to implement this, we can concatenate these two and we can have a different cases of inputs as 0, 0, 0, 1, 1, 0 and 1, 1. You can see I have used a case statement, and because of these two are single entities, I am combining this two as a 2-bit variable S and R. Now I can have a case of values 0, 0, 0, 1, 1, 0, 1, 1 combiningly. So I have a case statement with these 4 different cases, and Q will be equal to Q in this case, Q will be equal to 0 in this case, Q will be equal to 1 in this case, Q will be equal to Z in this case. This is the easiest way of implementing a flip-flop using case statement. Then comes the T flip-flop. In the T flip-flop, when T is equal to 1, output will be toggled. When Q is equal to 0, it will hold the state as I said in the SR flip-flop. This can be implemented easily using a if-else statement now. If-else code can be sufficient to implement this. First we need to check for reset. If reset, Q is equal to 0. Else begin. Again we are checking what is the value of T using if statement. If T is equal to 1, Q will be equal to not of Q. Q is equal to not of Q in the sense it is toggling its state. Means in the clock cycle, if the value of T is fixed to 1, the output will be changed to 1 over here. In the next cycle, it will be changed to 0. In the next cycle, it will be changed to 1 like this. To do that, just we can have Q is equal to not of Q like this with positive edge of the clock as a parameter in the always sensitivity list. So this part of code will execute whenever positive edge of clock comes. Similarly, we have a JK flip-flop where 0 0 is hold, 0 1 is 0, 1 0 is 1. The only change with respect to SR flip-flop and JK flip-flop is that this state. When 1 1 is the input, here in JK flip-flop output will be toggled, and in SR flip-flop the output will be high impedance to Z. So the same kind of code of SR flip-flop, but the only difference is the last state where Q is equal to not of Q for JK flip-flop for toggle condition. This is about the flip-flop implementation. Here what we need to understand is we need to use a always block, and we will be using a non-blocking operator here, and in the next slide I will be explaining what is blocking and what is non-blocking assignments. And before that we can have one more logic over here while writing the always and while writing the reset. There are two different ways of resetting the sequential circuits. One is synchronous reset, other one is asynchronous reset. What is synchronous reset and what is asynchronous reset means, suppose a clock signal is like this. If the reset is happening at synchronized with the positive edge of the clock, however the logic is synchronized at the positive edge. If the reset is also synchronized with the clock positive edge, then we call it as synchronous reset. Reset is synchronized with the clock. If the reset is independent of the positive edge, if the reset is somewhere here also, if the reset goes high, our device get resetted, then we call it as asynchronous reset. You can see the difference in the code. This is also a D flip-flop code with synchronous reset. This is a code with asynchronous reset. The only change is here. At the always sensitivity list, I am writing only pos edge of clock. This part of code, including reset, will execute whenever the positive edge of clock comes. But in the asynchronous reset, what happens? If we are going to add positive edge of reset or positive edge of clock over here, this becomes clock is independent and reset is independent. Means whenever the clock comes, there is no dependency for the reset. Whenever the reset comes, this part of code will also execute, and reset is equal to 1 means it will reset the things. That is how the asynchronous reset can be implemented. Whenever the reset is required, at that time we can apply the reset and do the reset. In the sequential circuit, if it is synchronous reset, what happens? It should wait for the clock positive edge to come. Even if you make reset is equal to 1 over here, it will reset at this position. You can see in this waveform, if you see the first thing, here the clock is changing at this position and reset is applying at this position itself, but the value Q is changing over here. Means it is synchronized with the clock at this position. Then in the second example, you can see reset is changing over here, but positive edge of clock is here. The D is changed here itself, right? That is the difference between asynchronous and synchronous reset conditions. Then we need to understand what is blocking operator and what is non-blocking assignment operator. Equals is a blocking operator, less than equals is a non-blocking operator. What this will do, these blocking assignments execute in series. Suppose if I have y is equal to a plus b, then I have some z is equal to a plus c, something like p is equal to d and with a, something like this. In this case what happens, and also I have one more condition that q is equal to y plus z. Okay, in this case what happens, first this y is equal to a plus b will be executed, then z is equal to a plus c will be executed, then p is equal to d and a will be executed. At the last this q is equal to y plus z will be executed. While executing this, it will take a recent values of y and z. Here y is updated, z is updated. With the updated value, this line of code will be executed. But while using the non-blocking assignment, the same line of codes, if you write y is equal to a plus b is written, and then z is equal to a plus c is written, then p is equal to some d and with a is written. Then the last line is q is equal to y plus z is written. In this case, what happens? All the lines of code will be executed parallelly, means at a time. This will not wait for the previous line to execute, right? So whatever the initial value of AB will be assigned to y, whatever the initial value of AC will be assigned to y, whatever the initial value of D ampersand A will be calculated and assigned to P, and initial values of y and z will be taken and assigned to Q. It will not wait for the updated values to happen. So y, suppose if it is initially 1 and z if it is 2, the value q will be 3. But y is updated to 5 and z is updated to 6, the value 11 will not get updated over here in q. That is the difference between blocking and non-blocking assignments. These blocking assignments, suppose if you have a 3 statements here, it will block these 2 until this completes. But non-blocking assignment, if you have 3 statements like this will execute parallelly. It will not block the execution of these 2 while executing this. That is the major difference between blocking and non-blocking assignment. To understand that, we can have a swap example here. We have 2 registers AB. Here also AB are the 2 registers. Don't worry about this. See, and while swapping the value of A is equal to 7 to B and B is equal to 4 to A, we require a temporary register here while doing in blocking assignment. Why? Because first A will be 4 and then B will be 7 is there. We need to keep this value of 4 to a temporary register, then do the assignment of B to A and then do the temporary register to B. This is the way we need to do. So you can see here B will be assigned to temp, then A will be assigned to B, and then A will be assigned with the temporary variable value. Why? Because if you do B is equal to A, whatever the value of A is 4, B will be also assigned to 4. Then if you do A is equal to B, already this B will be having 4, that will be assigned to A again. Means all the 2 variables or the registers will be getting the same value. We can't do that using only 2 A is equal to B and B is equal to A statements. We require a temporary register in between. But while doing it in the non-blocking assignment, A is equal to B will be written like this and B is equal to A will be written like this. These 2 statements will execute parallelly. Whatever there in B will go to A, whatever there in A will go to B. That's why we need to go with non-blocking assignments when we are dealing with the sequential circuits. Then we need to understand how to instantiate submodules in Verilog. Suppose a complex block of design we are making, and suppose this can be a kind of processor. This requires ALU, this requires some memory, this requires some registers, this requires some timers. All these are the submodules we can instantiate inside a Verilog main code, and we can generate the complex design. Let us understand that. To make that understand you guys, I have taken a very simple example of design of a full adder using half adders. In this case, first we need to have a code for half adder. You can see module half adder, sum, carry, A, B are the input and output ports of that. We can declare it as input and output here. Using simple assignment statement, here I have written the logic for half adder. A and B give us the carry. Similarly, A XOR B give us the sum. By using this half adder, now we can implement a full adder in this way. These are the 2 half adders required and 1 OR gate is required. How we are going to instantiate that means, you can see this part of the code can be instantiated over here. Since this full adder will be having A, B, C in as a third input, we require a second half adder. And A, B are the inputs, carry, sum are the outputs. Similarly, we have defined output and input now. Now comes how actually the instantiation is. This half adder name, directly we need to use it here. And this half adder will be having sum first, then carry, then A, then B. This first half adder is the instantiated over here with the name H0. You can see H0 is used here, right? This A will be directly mapped to A, B will be directly mapped to B. But the sum of the first half adder will be an internal signal. It is not allocated to any of the outputs over here. That's why this internal signal sum1 need to be represented as wire first. Then wherever we have a sum and we have instantiated over here, and this particular module is generating an intermediate output called sum1, in place of sum we need to write it as sum1, and it is generating a carry as well, but carry is carry 1. So in place of carry we need to write it as carry 1. It is an internal signal represented as wire. Then comes what is the input AB we are giving, means directly the full adder input AB we are giving as input here, that's why it is AB directly. Now we need to look at the second half adder, how it is. Second half adder is H1. Again we need to use the same kind of module name over here, half adder. Instance name I am giving differently, that is H1. This will be generating a sum, that is a complete sum of a full adder. That's why in place of sum here we will be having this variable sum. Then a second carry is generated from the half adder. In place of carry we need to have carry 2, that is carry 2 here. Then we need to assign the inputs in place of AB. In place of AB, sum 1 is the input and Cin is the input here. That's why sum 1 and Cin. Then comes one OR gate over here. This OR gate is required. So for the OR gate, what we need to do? Carry 2 is one input. This carry 1 is another input. So OR, O1 is the instance name. Carry will be the output. Directly we can take this, and carry 1, carry 2 are the internal signals which are generated by this half adder and this half adder. This is the way we can generate a full adder by using one half adder and other half adder, which is generated by a single module. This will be called as instantiation. We are instantiating a lower modules that has two half adders over here and here to generate a complete full adder. Now these two half adders will be connected internally with carry and sums, and finally the sum and carry will be generated. To have that internal connection we require these wires. Then the next thing is how we are going to write a test bench in Verilog for these designs. Test bench is very crucial component in Verilog to verify the functionality. So let us understand test bench aspects now. In the test bench, the very first thing is we need to write a time scale. Means why we need to write a time scale means in the test bench generally what we do, we will be assigning the values. Suppose if we take a full adder example, we need to assign a value for input as A, and then we need to assign the input as B, like this. After some time minute only, we need to assign the other value as A is equal to 0 and check for B is equal to 0. So these two different values need to be assigned with a time delay like this. But simulator will not understand this time delay, whether it is a second, whether it is a millisecond or microsecond. To do that, we need to have a tick time scale 1 nanosecond per 1 picosecond. This specifies whatever the delays we are going to write using hash will be in nanosecond, and suppose if we write 10.01, this will be the precision in picosecond. That is how tick time scale will be utilized. And then comes the delay how we are going to assign means first statement is A is equal to B, then we have a delay of 5 time minutes, then it is C is equal to A. If the time scale is written as 1 nanosecond, this 5 indicates 5 nanosecond of delay. Similarly, we can assign a delay for assign statements also in our design. Assign as 10 y is equal to A and B. This will be a time delay which will be taken before executing this statement. It will wait for the 10 time minute and it will execute this line. This is about the delays corresponding to assign statements. Then for the particular gate also we can assign a delays in this way. This gate statement will be executed after 10 time minutes. And as we know, we have seen many things in the sequential circuit designs. We will be using positive edge of the clock in always. This is a rising edge of the clock trigger. Whenever the positive edge comes, then only the action is taken. This is a timing operator here. Then comes positive edge of the clock. Then internally to the particular assignment statement, we will be having delay. These are all the different methods of assigning the delays. Then while coming to the test bench in Verilog, and the half adder design will be designed using assign statements like this, and the test bench will be having the variables which are input and output ports as in the design. You can see input A and input B and output sum and carry become wire and registers in test bench. Inputs become registers and output become wires. After that we need to instantiate our module, design module. half adder we need to instantiate it over here. Then we need to map these x and y to the inputs over here like this with the naming, and s and c will be mapped to the sum and carry like this. After that we need to provide the inputs to the variables x and y, that will go to the a, that will go to b, and design will generate sum and carry accordingly. So the main purpose of the test bench is to provide the stimulus as input to the design. This is the stimulus part. With the delays we are going to provide those, and that will be go to the design through this, and it will generate the output. And also to represent the values in our console or in the log file, we can use a $monitor, $display statements, and we can verify that manually by looking at the values. Then comes a test bench for the sequential circuit. Here JK flip-flop is an example taken, and as we know the functionality already discussed. So to have a test bench for this, the very first thing what we need to do is declaring all the inputs and outputs as register and wire accordingly. Inputs will become registers and outputs will become wire in test bench. Then comes the instantiation of our DUT. Then the very first thing is, first we need to generate the clock signal. Clock signal will be generated by using again always block, always begin, #5, clock is equal to not of clock. This gives us a clock generation. This clock will generate for a very 5 time minutes by changing its value. This 5 time minutes clock will be 0. Again this 5 time minutes clock will be 1. This time minute clock will be 0. This time minute clock will be 1. If you take a period of the clock, now it is 10, right? It is now it is a 100 megahertz clock. This will be calculated depending on the period, 1 divided by t. T is a period. Depending on that, the frequency will be calculated. And t will be #5 means it might be 5 nanosecond, it might be 5 millisecond. That will be defined by using a tick time scale, right? That is what we discussed previously. As soon as we as soon as we generated the clock, then we need to go with the reset generation. Then as per our requirement, we need to give the stimulus to the design. This is as simple as we saw in the previous example by generating the stimulus for the half adder. Similarly, we are going to give it for the sequential circuit kind of JK flip-flop. The very first thing is clock generation and then reset. Coming out of the reset, then give the different input values. Then, as I said, we need to understand how the clock generation happens in Verilog. Suppose in this module you can see a clock generator, a register clock 1, clock 2. There are 2 clocks to be generated here, and the time scale is 1 nanosecond per 1 nanosecond. Whatever the delay we are going to use throughout the design will be in nanoseconds. Initially, clock will be equal to 0 at 0 time minute. Here 0. Always #5 clock is equal to not of clock I am doing. Means for every 5 time minutes the clock value is changing. 5 time minutes in the sense 5 nanoseconds. If the 5 nanosecond is the change value we have given here over here, and it is changing its value from 0 to 1 after 5 time minutes, and here we are represented it as nanosecond, means it is 5 nanoseconds, and this also 5 nanoseconds. After 10 nanosecond get completed, it will be changing its value, correct? Now the frequency of that clock is 100 megahertz, period is 10 nanoseconds, right? And this will be having a duty cycle of 50%. Exactly, it will be having a half 50% of the on cycle, 50% of the off cycle in one period. If you want to change the duty cycle of that as well, we need to design depending on the percentage of duty cycle required. Duty cycle in the sense it is an on period, right, to the total period. Suppose if the on period is 70% we required, and other 30% of the complete period will be having 0, then it is 70% duty cycle clock. Always for every 9 nanosecond and 1 nanosecond, this value will be generated like this. This is having 9 nanosecond, this is having 1 nanosecond, this is 90% duty cycle clock. That is how it goes. And also we are going to finish the simulation by using $finish after some delay. This is the clock generation method using always. And also we can generate the clock using forever, you can see here, right? Forever and always do the same functionality, but the difference between forever and always is that forever can be used within initial, begin, end block, but always cannot be used inside initial. Always is separate, initial block is separate, but if you use forever to generate the clock, it should be inside always begin end. Then the next thing is arrays in Verilog. Arrays are very important concepts of Verilog to represent a memory. There are two different methods or types in Verilog, that is single dimensional array and multi-dimensional array. Suppose if we want a 6 element array, we can represent it like this. The name of the array first, array. Suppose array is the name of the array itself, and we need 6 element, means array of 6 we can write. The other method of writing this is with a verbose declaration, array of 5 down to 0. It means the maximum, it will start with the location 5 and it will end with location 0. You can see here it will be represented with a register 7 down to 0, my array 0 to 15. It means array will be having 16 elements. Each elements can contain 8 bit of data and 16 elements. So it will be having 16 elements like this. Each and every bit contain an 8 bit of data, 8 bit of data, 8 bit of data, like that. So this gives us a kind of memory where we can allocate a value to any position by assigning that index. That is single dimensional array. We can access the particular location of the array by selecting that address over here or the index. My array of 0 means 0th location, 1 means first location, like that. Multi-dimensional arrays. Multi-dimensional array in the sense it is having 2 dimensions. Means after the array name, suppose if we write it as array of 2 and then 3, it will be having 2 rows and 3 columns. So that is how the multi-dimensional array will be written. The first value what we are going to write here will be for the row, and the second value what we have written here will be for the column. That is the multi-dimensional array. How we are going to access this means by putting the 2 indices of the row as well as column. First row, second column, and the value. 0th row, 0th column, and the value. This is what the multi-dimensional array in Verilog. You can see here the 2-dimensional array can be represented like this. Suppose reg 31 down to 0, my array 6 to, if you are going to write 31 down to 0, give us each and every locations can contain 32-bit values, and this 6 give us we will be having 6 such rows, and 2 give us there are 2 such columns, and each and every location of the array will be represented with 0 0 is this, and 5 1 is this, 5 0 is this, 2 1 2 0 is this. It means array of whatever the first value we are going to write here will be representing the row, the next value we are going to write here will be representing the column, right? That is about 2-dimensional arrays. Then comes parameterized modules. I said a module can be written, inside that parameter can be defined. So parameterized modules are helpful in redefining the size of the particular bit, particular variable to a higher size or to a lower size. So you can see over here with an example. Module adder will be having a parameter defined over here as width is equal to 4. Parameter in the sense it is a kind of constant in Verilog. Okay, we are using parameter here for the width. So wherever we are going to use width, it will be having a value called 4. And in the input declaration, we will be having width minus 1 down to 0 for A. It means width is 4 minus 1, it is 3 is to 0. It means 3 down to 0 we will be assigning for A as well as B. Similarly for the sum, it will be 3 down to 0. This is present in the design now. In the design, we have AB for a 4-bit and sum is also 4-bit. Suppose when I am using it in a test bench, you can see over here we are instantiating our module. The module instantiation of the DUT will be done over here. Here we need to give the parameter value before connecting the variables of the test bench as well as the ports of the DUT. I need to provide the value for the parameter width with a hash keyword like this. Suppose if we give it as 8 over here and the parameter width is 4 over here, this design is made for the parameter with the value 4 and we are scaling up to 8 over here. It means in our design we have designed a adder which will take only 4-bit value. A is 4-bit, A is 4-bit and B is 4-bit, right? Suppose if we want this sum to be generated with 8 bits for the 8-bit of AB, we can scale it up while instantiating this module in a top module, right? This is a 4-bit module designed with a parameter called 4. It can be incremented to parameter 8 when we are instantiating this in a complex module. This can be possible while using the parameterized modules. That is one thing. Then comes the parameterized RAM design. You can see while designing a RAM, as I said, we need to use the register, right? This RAM module will be having a clock signal first, then it has a reset signal, write enable to do the write and read functionality. Then we have a chip select. If chip select is equal to 1, then only this memory will be useful. And data in to write the data into memory, and which location we need to write, that is address. And data out is with the same size of data in, we are going to provide the read output. Suppose if you want to design a 1 kilobyte of memory, it requires 0 to 1023 locations. It means total 1024 locations. Each and every location can store 8 bit of data. In such requirement, we need to go for a register by declaring that memory which will be having 1024 locations as a array. Array of 1024 give us 1024 locations, and that we need to provide with 8 bit, so it is 7 down to 0, right? So what I mean to say is 7 down to 0, any array can be a memory here, memory of 1024 is a simple representation, and it will store, it will be as a register. This will be a memory of 1024 locations with 8 bit insides. So you can see over here, register, data width -1 down to 0. This gives us the number of bits we need to store. Since it is 8 bit, data width -1 in the sense data width will be a 8 over here. You can see data width is 8, which is parameterized. Means we can scale up this memory to 2K also by changing this. That is what the meaning of parameterized RAM over here. But for now, let us take it as 8, and 8 -1 down to 0 will be 7 down to 0. It gives us 8 bit data inside. And then we have 2 power 2 double star address width, in the sense address width is 10 here, 10 in the sense 2 power 10 give us 1024, right? So here 1024 minus 1, that is 1023 colon 0 is the array representation. So it will be having total 1024 locations. Then depending on the address bits and the data width what we are going to give, we can scale up and scale down the size of the memory. And obviously, depending on the values we are going to give here, this register is going to be modified, and write read operations will be similar to 1K and 2K. You can see always at positive edge of the clock or positive edge of the reset. When reset is there, D out will be equal to 0. Else, we need to check for write enable is 1 or not. If the write enable is 1, we will be doing the write operation by writing memory of that particular address is equal to the data in what we are going to get. This is write operation. For that, we need to check for if write enable is equal to 1 or not, write enable. Else in the sense we are checking for write enable is equal to 0. In that case, we will be taking memory of address, then we will be assigning to D out. Here these operators are, it is non-blocking operators. It is misprinted like this. Please treat this as less than equals in this way. This is a design of parameterized RAM, which can be scaled up by changing the data width as well as the address width, so that the register, which will be act as a array of registers memory, will also be scaled up. Then we have task and functions in Verilog. This is a very important concept in Verilog to do the repetitive functionality. If the piece of code is written as task and function, we can use it in different places whenever it is required. But the only difference between task and function is that this task can be used whenever we have delay on the time consuming events in our task. In the piece of code we are going to write, suppose it is taking much simulation time, then we can go for task. Suppose if the function is written where there is no delay statements can be written. Whatever the function we are going to write will be specifically for the simple calculation that give us the result through the function name itself. But this task can have a delay statements. It can have multiple input and outputs inside a task, and task can be invoked inside a task and end task keywords. And we will be having a facility that inside a task we can trigger the functions as well, correct? Since it has a delay statements as well. But inside a function we can't trigger a task. Why? Because function cannot contain any delay statements, but task might be having delays. That's why inside a function we can't trigger any task. That is the disadvantage of a function. To have an example of a task over here, you can see this is a module which will be calculating zeros in the number of bits in the data. Suppose the data width will be 8 over here. There is data 1, data 3. We need to calculate the number of ones present in that. For that we have written a task over here. You can see with keyword task, count number of zeros in a byte, and here the input is 7 down to 0 data in, and count is 3 down to 0. We will be having a count for each and every bits of the data in. Integer I is there to have a count over here, and begin and end within the task give us initially count is equal to 0. Then a for loop starting with 0, it will go up to 7, and then it will calculate, it will check for whether data in of I will be having 0. If so, count is equal to count plus 1. Otherwise, it will increment I and again check for 0 in the data in of 1. Then data in of 2, data in of 3, data in of 4, 5, 6, 7. It will count till 8 values. If any 0 is there in the 8 bit, if 1 0 is detected, it will increment the count. This is a part of task we have written. Then we need to call this task whenever it is required to calculate the number of zeros in a data in, and it will provide the output in terms of count. How we need to call this task? In the same way of instantiation, you can see count zeros in a byte. First input need to be given as data in, that is data over here, this data, and we need to give another input called count. That count will be output here. So one time we have used. For other data also we need to calculate the same thing. For that we have used one more time. Other data also we need to calculate the same thing. So 3 times we have used this same task, right? But here the inputs in place of data in are data 1 and data. This can be data 3, right? And it will be generated to the output out. This is a simple example for a task. Then similar example we can check for a function. Here what happened, we need to wait for the 8 cycles so that it will calculate and give us the count. Suppose if we have a delay over here also, it will take and calculate the values. But in the function, you can see, suppose we need to calculate the parity of some 8 bits or 32 bits like that, we can go with a function like this. Parity in the sense, we are just doing XOR operation of those and give us the result of 1 bit. You can see module parity, register address, and 1 bit output taken variable is parity. And within the always block, we can see calculate parity is the name of the function here defined. We are calling that and giving the input address as a input variable over here. Input argument. This function will be consisting of one input. Remember, function will not be contains any output variables. Function will replay or return the value of the result of this through the name of the function itself. Okay, you can see in the logic of the function, calc underscore parity itself is the name of the function. It will calculate by XORing the bits of the address, 32-bit address. So here 32-bit address is the input parameter we are going to give, and once we give that and call parity, it will give the result through this call parity name, and here is the result. We are going to get it to the parity. That is how the parity will be calculated using a function. Here there is no delay statements are going to be used, that is not allowed. Then we have compiler directives in Verilog. Compiler directives, as the name says, these things are going to be executed at the time of compilation itself and tell the simulator that this is the way we need to go with in this code. Sometimes some part of the code need to be executed, sometimes some part of the code need to be neglected. In such cases, we will be use this compiler directives to direct the compiler or the simulator to indicate that this is required. You can see we have tick define. We can use it as some constants or to define something. Then we have tick include. This will include the entire content of file into the module. We have if def or if and def. If something is defined, then only include this code. If something is not defined, don't include that. And timescale we have seen already. All these things will be executed at the time of compilation itself. You can see define and if def here. we have a include file nar underscore dut. We have directly instantiated over here. This is a different file. This module dut is one module. Similarly, we have another module of module nar underscore dut. Okay, this nar underscore dut, we need to include it over here while using it as an instantiation in a top module. This is top module dut. Inside that we will be having nar dut as well. In such case, we need to write a include file. Then only compiler will take this and compile it. Then we have ifdef. Ifdef in the sense we have a define over here and underscore op. If it is defined like this, then only this part of code will be executed. Otherwise, it will go to the else part and execute this line of code. If we neglect this defining this, it means don't consider this line of codes at all. Directly consider these things for simulation. That we are telling at the compiler at the time of compilation itself. If it is defined, use this, and if it is not defined, use this part of code. This is much helpful in defining the things and considering the things of part of code for simulation and synthesis. You can also do these defines through the command line using Cadence or Questar, Synopsys VCS tool or iCarus Verilog in this way. Then timescale we have already seen. We need to define the timescale at the starting of the code itself to make the system understand what is the delay we are providing and what is the precision of that and what is the unit of that. This is about the compiler directives. Then comes the difference between Verilog and system Verilog. This is the things what we have seen so far with respect to Verilog, but the advanced version of Verilog is system Verilog that will be used for verification. System Verilog will be containing all the constructs of Verilog what we have seen so far, and also it consisting of some OOP concepts. OOPs concept in the sense it will be having inheritance, polymorphism, abstraction, and all the OOPs features which we are going to use, classes, dynamic arrays, associative arrays, will be useful in verification of these designs written in Verilog. That's why for the verification, while writing the test bench, we will be using system Verilog. That give us more flexibility to give the stimulus in a different way by using object-oriented programming, and that feature is much helpful in verification methodologies. That is about Verilog and system Verilog introduction over here. In the next subsequent lectures, let us see different concepts of Verilog in detail and also system Verilog. Already a playlist with respect to Verilog, system Verilog and UVM is created in my channel. Please visit them and understand how the system Verilog is used for verification and how the design will be made using Verilog, and also a UVM, that is universal verification methodology, which is using in the industry currently for verification. This is all about the Verilog session over here, and in the next sessions let us see more concepts like this with respect to VLSI. Thank you.